Swayam Prabha. Digital India. Educated.
Hi, welcome back to this lecture series on foundations of cyber physical systems. So, we have been giving some introductions to different cyber physical system aspects, right. So, what we will start with is basically what are the compute platforms that are typically used in cyber physical systems, and what are their attributes due to which they find their applications in such systems. So, from this point, it's basically going to have the properties of real time and embedded systems only, because CPS compute platforms have typical workloads like onboard computation, depending on of tasks like control law, signal processing tasks, estimation tasks, etc., and we need to perform them inside some power budget as well as a time budget. So, the typical choices here are RISC CPUs, which by design are very simple and low power, and also power optimized microcontrollers like Atmel and several other vendors. So, we have just a picture of the Arduino Uno board, which is kind of extremely popular for DIY type experiments here. So, this is a choice if you are doing some home project of CPS at your home or at a lab scale. These are very low cost boards available with lot of interfaces to like USB, serial port, Ethernet, and you can have a general purpose GPIOs through which you can connect and create some projects like motor control or other kinds of CPS projects like door locking, autonomous vehicle, etc. So, most of these low power chips that came around came with this RISC computing philosophy. RISC is reduced instruction set computing. That's a term which was standardized in Berkeley by Berkeley and Stanford around 1970s, and also it involved inputs from IBM, right? And the basic architectural model had some philosophies, which was that, well, previous to this, whatever computer architectures have evolved, they followed what they called as the complex instruction set computing. That means the instructions could be of any size, they would be quite complex in their encoding, and they can be also of any length. So, what these people said, researchers at these universities, what they said was that you should build a CPU where the instructions should always execute in a single clock cycle, and the instruction encoding will be simple, and all the instructions should have a same length to make the instruction set very regular. Okay. Not every instruction will have the power to access the memory. Every instruction will operate on operands that are in the register file, apart from load and store instructions, which will have the power to bring data from memory or store back to memory. So, the execution units are like pure hardware. There is no lower level microcode software that is going to execute, and this RISC computing standard was adopted by IBM in their 1970 this series of CPUs. Okay. So, on this basic philosophies, RISC CPUs have been built, and the simple nature of the CPUs also made them low power, and embedded processors became the first line of things where this computing philosophy was adopted, and nowadays it has slowly moved in, the RISC philosophy has slowly moved into the desktop world also in several ways. So, the idea is that since the processor is simple, the hardware implementation is very simple, the instruction set is simple, the number of instructions is less, and execution of each of them will happen in a single clock cycle. So, that makes the chip small and low power. But the chip will have a large register file, because all instructions apart from load and store are now going to work on data which is there in the register file, and the on-chip cache size will also be high. Again, I require this because most of the instructions will work on register file. That means for any data you will need to access the memory through loads and stores, and you will like to have a large cache so that you don't need to go to the memory that frequently. And also slowly RISC processors started becoming superscalar. That means they can execute multiple instructions at a time, and that would need support for multiple functional units like multiple adders, multiple floating point multipliers, and other kind of functional units. A classic RISC pipeline would have these following stages in its computer architecture. So it would have a fetch stage through which the instructions are fetched. Then the instructions go for decoding. The decoding phase, so the fetch stage will see that what the program counter is pointing to which instruction, and that would be getting loaded, and then that will be passed to the decode stage of the pipeline where the meaning of the instruction will be decoded, and accordingly the hardware data path of the CPU would be activated. Suppose you want to execute a multiplication, then the ALU will take as operand to registers, operands from the register file with suitable select lines being turned on, and it will do the multiplication. So that would be in the execute stage where the ALU operations will happen. Then in the memory stage, suppose you have a load and or a store instruction, the load address or the store address would be computed in the execute stage, and the actual load and store, that means the access to the memory to load data to the register file or to store data to the memory, that would happen in the memory stage. And finally in the register stage or the write back stage, as more popularly called, the register file will get updated. So just a correction, this is more popularly known as the write back stage, where this functionality actually happens, that is the register file gets updated. So this is the classic RISC pipeline of 5 stages, and typical data bus width for RISC CPUs would be 32-bit or 64-bit. That would mean that all instructions, since this is a 32-bit or 64-bit CPU, that is the instructions would also be of this size. Okay, so and all the instructions would execute in single machine cycles. That is one of the RISC features. And like we said, that the only instruction, so just to summarize, this is the important thing, and then all instructions would have same length, and the only instructions accessing memory is load and store. Typically you will have a large register file to support more number of register based operands, and the instruction set should be sufficiently simple and small. So this is a block diagram taken from a website mentioned here of one of the earlier RISC processors, R400. So you can see several blocks like CPU registers, floating point registers, data cache and other stuff, and control signals for the pipeline. And similarly here we are just trying to tell you that, well, it has a large register file of 32 registers for general purpose usage by the processors. So the point I am trying to make here is, we are not here to teach you computer architecture. We are trying to tell you what are the properties of RISC CPUs which help them to compute for an embedded processor in low power. I mean, that would, because to compute in low power would also mean that the processor should be sufficiently simple and it would have certain kind of specific features. So we are just trying to give you an overview of a basic computer architecture at a very high level, assuming that this course is the interdisciplinary one. People will be coming from various backgrounds. They may not understand that how how an embedded processor works in a low power mode and what are its typical characteristics. So we are just trying to give an overview here. So the different kinds of instructions that the RISC CPU will execute will roughly be of this type. It's a load store instruction, data storage to the memory, or bringing data from the memory to the register file, working on register file data to do some arithmetic operation or some logical operation or some jump of operation based on conditional ifs, or some coprocessor instruction. Let's say I have a separate FFT chip where I will offload data from the CPU and ask you to do some FFT computation and give me the result, things like that. This is a simple example again taken from this resource where we are trying to show a very simple 5-stage RISC pipeline, where you can see that the data path has been built with the ALU and the register file, etc. The program counter, different muxes are in place, right? Now just to give an idea that what are the other things that may be present in an embedded processor. For example, nowadays embedded processors are having a large address space. So that would mean that they require a large address space, but since the physical memory is limited, the idea of virtual addressing, which is prevalent in the desktop domain, is also now prevalent in the embedded domain. So that would require some special hardware to do virtual to physical address translation, which is the memory management unit, and that has now found its way into embedded processors also. So in many embedded processors you will see, for example, modern ARM processors from ARM, they have MMUs. They also have the translation look-aside buffer, or the TLB, which is like a cache which stores the last frequently done virtual to physical address calculation, so that the MMU's translation hardware can be bypassed. So just in a summary, if I am trying to say the differences between embedded kind of computing and desktop kind of computing, the CPUs are simple here. They have more number of general purpose registers, instructions encodings are of the same length, and the hardware design is simpler with single cycle instructions. And the issue is something like this, that I would rather not say it's code quality, or because I would rather say the code size. The issue is when I have very simple instructions and the number of instructions is less. Suppose I am implementing a C function in RISC processor and in a CISC processor, the application binary that will be generated here will typically have a very large size, whereas the one here can have a small size. The reason is you have very simple instructions. So for doing a complex operation, you will need multiple simple instructions. Here you may do that complex operation using one such complex instruction, which is anyway here, right? So that would mean that the code size of the assembly file that you have will be larger, right? But again, this makes the simple instruction approach makes these CPUs low powered and simple, and they have wide applications in the CPS IoT domain. So when I say simple and complex instructions, let's take an example. Suppose I want something to happen like this, that at some memory location M1 there is some data, and at some memory location M2 there is some data. I want to add them, and I want that data to go to some memory location M3, right? There may be a CISC instruction which does this. So there is one instruction, let's say in CISC, if you execute that, it will internally do all these things through suitable hardware lines activation. But if I am trying to do this in RISC, I have to first have an load instruction which will bring data from memory M1 to some register, another load instruction to bring the data from M2, one add instruction to load those two data points that have been brought to the register file and store the result in the register file. Okay, so if I just write it, so you see these are the number of RISC instructions I will need to execute here. So that's an idea that why this code size should actually increase in this case. Now, so the processor is one unit. Along with that, you need to have the memory. Now, going into the very basics of memory, let's understand how a bit is stored. So in a simple DRAM cell, the bit is stored by pass transistor logic like this. So whenever a word is written, so this is high, right? So this switch will close, and this capacitor will store the charge, and so that's like one bit being stored. So this is a DRAM. That means whenever it's powered off, the capacitor will lose the charge. Whereas in a static RAM, the SRAM, you will have a more complex design like this. So again, we are not getting into the details. There's a VLSI subject. We are just trying to give you an idea what it is. Now, when I talk about DRAM, what is important from this to understand is with time this capacitor may lose charge even if it is powered on. Suppose the word has been written, the DRAM is on, but now no word is getting written. So the capacitor is by principles of physics is going to lose some charge, right? I mean, nothing is lossless here. So the DRAMs have to be refreshed with some period. So suppose I have written a 1 value here, and then I'm not changing that value. What will happen is this bit is going, its charge is going down. So after a period of, let's say, 10 seconds of milliseconds, I mean some number of tens of milliseconds or 20 milliseconds, I will have to do a refreshing here, so that the capacitor charge, which was actually trying to represent a 1, should again go to this refreshed higher value, right? Now the point I am trying to impress upon here is the DRAM, when you have it in your system, it needs to be refreshed, and this refreshing can lead to some loss of bandwidth. Let's understand. So take an example here again from this book. So what's happening here is, let's say you have a 256 MB DRAM chip. It's organized in this way externally. That means the external interface is like 32 across 8, but internally it's an array 16K cross 16K. That means in each row there are 16K locations, right? Now these rows must be refreshed at least once every 50 milliseconds so that the data is not lost. If you have some capacitors charged and if you have not refreshed them inside this 50 millisecond time, the capacitors are going to discharge out. So you need to refresh them. Now let's say refreshing each row requires 100 nanoseconds. So the question is, well, this DRAM bandwidth, how much of this I am going to lose to such refresh cycles? So if I have to refresh all these 16K rows, what is the time required? The time required would be 16 times 1024, that is 16K, times 100 nanoseconds, so that is 1.64 milliseconds, right? So this is the total time that is required to do the refreshing of the entire DRAM, and this thing I am going to do again and again, right? So I am losing this time out of every 50 milliseconds, because I am going to do the refreshing again after this 50 millisecond cycle, after 150 millisecond cycle. So inside this 50 millisecond time cycle, for doing the refreshing business, I am losing 1.64 milliseconds. So that means whatever is the memory bandwidth, the read-write capacity, read-write speed of the DRAM, out of that, this 3.3% time goes to the refresh, because during the refresh no read or write will happen. Any data that is coming for read and write will be kind of stalled in the buffers, and they will happen after the refresh, right? So the reason we have this calculation here is we are trying to say that when a processor is computing over some data, there are several ways time has to be accounted for. Time will be accounted for when the processor has to bring data from memory. Time has to be accounted for when the processor has to bring data from the cache, and time has to be accounted for when the processor has to execute instructions. So we have a RISC CPU with simple instructions, all of them are single cycle. So executing those instructions will take their own time. Depending on the input, it will depend that which sequence of instructions are actually executed. So at different instances, the same code can have different execution times in the CPU, and there will be time spent for accessing the main memory, and there will be time spent for accessing the cache memory. So when I am trying to find out what is the actual time consumed by this code, or I am trying to figure out in the worst case what is the time that is going to be consumed in any run of a control program on a CPU, I have to understand what is the components, what is the computer architecture components in the CPU, and what are the latencies that can happen due to them. So that's how all these things are connected. If I am trying to do some timing analysis of a code, which is very much required when I am trying to figure out, well, due to execution of a code inside a control loop, what is the delay that is created. So that is the linkage, right? So we need to understand how all these basic computer architecture events take up time. Okay. Now the other thing I just mentioned is cache memory and accessing that cache memory. How is time taken? So just to understand that what is the impact of memory. So this is like the curve which tells you that how processor frequency has increased, but how memory performance has not increased that much, right? So there is this processor and memory bandwidth gap. So no point really in making the processor fast unless we can increase the speed at which we can do read and write from memory, right? So this speed gap between the memory and the CPU has to be hidden in some way, and there are ways to hide it. Memory can be slow, but memory can be accessed through a wide bus. That is the advantage of having a memory. So although we can have a 32-bit CPU, that means it is going to crunch 32-bit data, okay? The data bus may be 32-bit, but the memory, the instructions may be 32-bit, but the memory can be read in chunks of data which is much wider than 32, maybe let's say 32 cross 4, something like that, right? So there are two possible techniques here. The memory is wide access, and this wide access of data there is connected to a buffer, and that buffer from that, so multiple different locations of the memory are accessed, they are in the buffer, and from this buffer which data is to be forwarded can be selected through a bus, and then there is through a mux, and then the output of the mux is connected through a narrow bus to the processor. The other option is have a wide access memory, have a wide access bus, have this buffer and the mux on the processor side. So depends on your choice to hide this gap between the processor speed and memory speed. The other option is the memory is divided into banks. So when you are writing consecutive data addresses, you write in different banks. So if you are writing in different physical banks of the memory, those writes or reads can occur in parallel, right? So that's another advantage. Now the question of memory hierarchy. So we'll just take very small time here. So this is a rough idea of how the memory hierarchy is. So you have main memory, you have the hard disk, the secondary memory, you can have tape drives as the tertiary memory. As you can see, and from the main memory you can take data to the level 2 cache. From the level 2 cache you can go to level 1 cache, and from there you can take the data to the CPU register, right? So these are the things which are inside the CPU chip, and they connect with the main memory, secondary memory, tertiary memory, like that, right? Now the question is, if you see, if you go higher in the pyramid, the cost per unit of memory drastically increases, but what decreases is the access latency, right? These are fast memory elements due to two reasons: the technology used and their nearness to the CPU pipeline, right? And also points like whether they are on chip or off chip, stuff like that, right? So the overall point is I cannot have a very costly memory segment for doing something in large amount, right? It may be a cost issue, it may be also a feasibility issue. So this motivates why I need some cache memory to get data from the main memory. So the cache memory helps me to hide the memory access latency, because whichever data I will use, once I bring it to the cache, which is a faster memory, whereas the main memory is a slower memory, if the CPU requires that again, I can just quickly get it from the cache. And the idea of caching also follows from basic principles like the principle of locality, right? Whenever I am doing, and the locality can be both spatial and temporal. So I can, when we write programs are more likely to fetch the same data again and again over time, and also the program is very much likely to fetch nearby locations to whatever has already been accessed in future, right? So these principles motivate the usage of cache memory. So this is a faster memory than the main memory. So whenever I am executing instructions, I can bring data from the main memory, store them into the data cache, and then I can access them, so that in future I will need the same memory, same locations data, I can get it just from the cache instead of going to the main memory. So some small math here. So let's say I have a single level cache, there are no multiple levels of cache, and the hit rate of the cache is h. That means if I request data from the cache 100 times, out of that h number of times the cache will have the data, so that would be a cache hit. Otherwise the cache would be it would be a cache miss, and I have to consult the main memory, I have to get the data, and I have to store it in the cache, and then I will also use it in the CPU. Okay, So, the effective cache latency in this case can be calculated like this, where C fast and C slow represent the latencies in case of a cache miss and a cache hit. Okay. You can also have multiple cache levels. Suppose you have a 2-level cache, and at each level you have different miss penalties. So, you have a level 1 cache with a hit rate, let us say like this, a level 2 cache with a hit rate like this, and the miss penalty in level 1 is small because then you only go to the level 2, and the miss penalty in level 2 is large because then you have to go to the main memory. So, you can see those access latencies are here as 8 cycle and 60 cycles. So, then the effective latency can be found using some formula like this, right. So, here C fast, C medium and C slow tell you that what is the in case of L1 hit, what is the time consumed, in case of L1 miss but L2 hit, what is the time consumed, and in case of L1 hit and L2 hit also, what is the time consumed. So, this is for the L2 miss, sorry, in this case of L2 miss, what is the time consumed. So, using them I can calculate what is the effective latency here, right. So, typically you can see that if you use a multi-level cache system, it can be also shown with some simple examples that they actually help you out. Instead of having a single cache, if you have multiple levels of cache, that means that you have to access the main memory even less number of times. Okay. So, you will have so from this you can just calculate an overall hit rate. So, using such cache based systems, you can also hide the memory latency, and all these techniques of hiding the memory latency are useful for meeting some real time deadline. So, that is why it may help to have multi-level cache systems even in embedded processors, and nowadays they also have such systems in basic RISC CPUs which are typically used in such applications. So, this is one small example which you can just study, that we are trying to figure out what is, suppose a system has a CPI of 1.2 considering there is no cache miss. Now, if I just consider a real system where there is really cache miss, and whenever the cache miss happens, these are the miss penalties, this is bound to increase the cycles consumed by suppose I am executing 100 instructions, and then the number of cycles consumed in case of no cache miss will be something, right, which is an ideal thing, right. But when there are cache misses, then the miss penalties will add on and the number of cycles will increase, right. So, let us say there are no cache misses, the CPI cycles per instruction is 1.2. Now, suppose there are 100 instructions, and let us say the number of memory accesses happening on the average per instruction is 1.1. That means for 100 instructions there are 110 memory accesses. Now, the cycles where you do not have miss is this 120 cycles, right. That means because these are the cycles where there are no cache misses, right. Now, these are the CPU's instruction execution cycles, okay. But now you have this 110 memory accesses, right. So, for this memory accesses, so if you look into this problem, what it is saying is, here in this CPI calculation the cache misses are not accounted for, right. So, they need to be accounted for by considering these memory accesses, okay. So, you consider this memory accesses which are numbered 120. So, from this you can calculate that how many L1 misses you are going to have and how many L2 misses you are going to have. From this number of L1 misses, you can figure out how many cycles will be spent in accessing the L1 cache and how many cycles will be spent in accessing the L2 cache. So, those will be added to this 120 cycle ideal CPI where no cache miss was actually accounted for, right. So, these are the extra cycles which are spent by doing the memory system access, right. So, what you have is 120 plus 110, right. So, that means your effective CPI becomes 2.3 here instead of something like 1.2 where the cache misses were not considered. So, overall I can calculate what is my hit rate. So, that would be 95% of L1 plus this 80% of 5%. So, this is my overall hit rate, and my miss penalty also I can calculate, it would be 60 cycles. You can just follow these effective latency equations, and this miss penalty we have already seen here, right. So, with this we will end our discussion on basic CPU architectures and memory systems which are used in these systems. We will end this lecture here. Thank you.